This one. Is that the one you're talking about? All right. So what I would do is this. I'd open up Excel. Okay? And the fact that it's, I would exploit the fact that this is on digital format to do this. So I copy that, I paste it, right? So I'm going to take this, because it's a little bit easier to deal with something that's all right. So now looking at this, let's see, is this right? So it looks like this is it's reading us as text. Why is that? That's so weird. Nice. Okay. So here is, let's see, is this, yeah. Place all, okay. So here is your data. Let me enlarge this. And let me go and insert a scatter plot, select the data, add the series. This is S versus T. My S value, my X values are my times. My Y values are my speeds. Okay. And there you go. And now it gives me this curve. And guess what I'm going to do? I'm going to select, what is this? Select chart style. Change chart type. And maybe I'll do something like that. And there you go. No, that's not what I wanted. I want a smooth curve. Okay? And now I would just use that as my baseline to then go and graph tangent lines. So notice how quick that was, right? I didn't get my hands dirty trying to graph this thing. All right, other questions? So looks like you guys had a pretty easy time doing the homework. I think if you spend more than 180 minutes on all those problems, just email me. You don't need to spin your wheels that long. Email me. Like the lowest time, the shortest time I saw was about 70 minutes. And that seems about reasonable for problems of that caliber. So yesterday, I proved the first kinematic equation. Everybody remember what it said? It said that the change in position, right, is equal to the initial velocity times t plus 1/2 at squared. And it's important to realize that this is true only for what? Under what condition is this true? Yes. Yes, uniform accelerated motion. And you'll see at some point in this course we're going to be dealing with non-uniform accelerated motion. But right now, the task is to actually get used to uniform accelerated motion. Now so this is what I call the first kinematic equation. Then there is the second kinematic equation, which I'm going to justify now. So I'm going to draw up a velocity time graph. So here we go. Here's a graph, and let it be a line. So here's a line. So clearly, what type of motion is this? Well, we don't know because guess what I haven't done? Specified anything about it. So it's a velocity time graph. What type of motion is this? Yes? Uniform accelerated motion. And so what can I say? Let me actually extend these axes. So if this is VF and this is VI, then there's going to be some point where what's going to be true? There's going to be some point where this thing has an average velocity. And what is that point? What is it? The midpoint. So in other words, V bar is equal to what? VF plus VI over 2. I don't know if you can see that. So I'm going to draw this point. So that is VF plus VI over 2. So if this is happening, if all this is happening over some time t, this is time, then what can we say? Well, we know that the displacement is the area under the curve, correct? So what can you say about the area of that rectangle? Anyone? Yes?
It would equal the area under the curve.
Correct. It's equal to the area under the curve. How do you know this?
Because the triangles cut out of the same.
What gets included in the rectangle is precisely equal to what is excluded under the curve. So therefore, those two areas are equal. So let's actually investigate what those two areas are, or specifically this rectangular area. It has a height. The height of this rectangle is equal to what? Yes? And what's its width? Delta t, or t, is the area. Correct? So now let's zoom in, or zoom. So the area is VF plus VI over 2, right? And the time, the change in time, is just delta t. In this case, delta t is simply t. So, but the area, we know this from before, is equal to the displacement, which is delta x. So now what can we do? Well, consider this. For uniformly accelerated motion, the average velocity is equal to the instantaneous velocity. In other words, A is equal to VF minus VI over delta t. Correct? So what I'm going to do is I'm going to rearrange for delta t. We have delta t is equal to VF minus VI over A. So what do I have here? I have that VF plus VI over 2 times delta t is equal to delta x. I'm going to plug in for delta t. What do I get? I get VF plus VI over 2 times VF minus VI over A equals delta x. So, what can I do now? I can FOIL the VF minus VI and the VF plus VI. What do I end up with here? Yes? Correct. This is called the difference of squares factorization. And so sometimes you'll see this arranged in various ways. The way I usually write it is VF squared minus VI squared is equal to 2A delta x. So now we have our kinematic equations. This is what I call the second kinematic equation. Because obviously that's not trivial. In other words, it wasn't trivial exercise. It wasn't like a rearrangement of a definition that allowed us to do this. We had to actually do a little bit of work to come out with this equation. So the second kinematic equation says VF squared minus VI squared equals 2A delta x. Remember, all these things are functions of what? All of these variables, v's or a's, are functions of what? Time. So keep that in mind. All right, now we're there. Oh, man. Open up to lecture problem number 8. And what's equally interesting is, like, for me, this relief of finally getting there will only be equaled by my relief of leaving kinematics entirely. Yes. Like, I can't wait for Unit 3. Unit 3 is like it's just awesome. I mean, you guys are touching the mind of Newton. Do you understand how brilliant Newton was? And the guy was sick. All right. So, anybody want to read this? Last year. So, you have a truck and you have a car. The car accelerates for 2t seconds. The truck accelerates for t seconds. I have no idea why that just happened. However, the car accelerates for a time of 2t seconds while...
And wow, the t seconds whereas the truck accelerates.
All right, kill the while the t seconds.
The end wow, the t seconds?
And kill the and as well. All right, so there you go. Sorry. Excuse me. You'll see why. Because in the second homework set, you're going to have a variation of this problem. So, what's the easiest approach to this? How do you find the distance of the car compared to that of the truck? You think just, how'd you infer that?
Because, I mean, that's like, in the reading, like, anytime it's doubled, it's 4 to 1.
Okay, and that's true. That's certainly true. Simplest way to do this formally is to graph it. So let's graph it. What does this look like? So I'm going to graph the truck like this, and I'm going to graph the car like this. All right? So that's the car. Maybe I'll do the truck in like this. All right, can you guys see this? Let me see. Can you guys see that? So this is a V versus T graph. Now the displacements of each are going to be represented how? Yes? Area under the curve. And so this right here is going to be what?
1/2.
What is that going to equal? What is that going to represent?
Oh, the distance. Yeah.
So this is the displacement traveled by the truck, correct? So this right here is dt. So then what's dc? Yes? So in other words, dc, the displacement of the car, would be this whole thing. Correct? So, I'll use... So that's dc. So now what can you do? Well, watch this. By symmetry, I can go and start ripping this thing apart as follows. One triangle, two triangles, three triangles, four triangles. Notice the displacement of the car is 4 triangles, whereas the displacement of the truck is 1. So there you have it. So geometrically, yet again, you get a very elegant visual solution, where DC is 4 triangles, whereas DT is just 1 triangle. More formally, the displacement of the car is going to be 1/2 a times 2t squared. The displacement of the truck is going to be 1/2 a times t squared. This would be the algebraic formalism. So if I wanted to find the ratio of the two, what would I do? Just divide them. In other words, you get dc over dt is equal to what? What happens to the 1/2 a's? They all cancel. 2t quantity squared is equal to 4t squared over t squared. What happens to the t squareds? They cancel as well. And you're just left with 4. Pick your poison. Sometimes you can come up with a geometrically elegant solution. Other times, it will be an algebraically elegant solution. Next problem. What does the next problem say? Wait, what are we doing? Simultaneous watches, right? And they were separated by a second. Why did I do this exercise? Because guess what you're going to have to do for this problem? Same thing. Call one of them t, call one of them t prime. So what do you have here? So one of them is a car. What's a car and a cop, or car and a cop? So TC and TP. And the question is where do you want your 0 to be? Meaning, what happens? When do you want your time equals 0 to be? When your cop starts driving, or when the guy passes the cop? I prefer when the cop starts driving. Why? Yes? Yeah, but why? What is the cop doing that the other guy's not doing? Accelerating. That's right. The cop's accelerating. Which is a more difficult motion to describe? Uniformly accelerated motion or constant velocity motion? What's more difficult to describe? Really? Constant velocity is more difficult than uniformly accelerated motion? No. Uniformly accelerated motion is more difficult to describe. Why? Because your velocity is constantly changing. Constant velocity is as easy as it gets. So, what we have is that T of the police officer, which I'll call TP, and then you have TC. So the TP is, I'll just call that T. And the question is, what's TC equal to? Yes? Is it T minus 1? If the cop's watch is at 0, what is the car's watch at? Plus 1. That's right. And the best way you do this, I'm telling you, best way to do this is just count it out. You say, I want that cop to start at 0. Well, if the cop starts at 0, the other guy's already 1 second ahead. So he's at T plus 1. Is everybody? Yes? That's well, let's hold off. Because I haven't talked about where my position, where my coordinate system is. So let's do the coordinate system. So where do you want to put the origin? At the police car. So we're going to put the origin at where the cop is. Okay? So now the police officer is going to accelerate, which I'm going to indicate by a double arrow. So this is the police officer. Where are they going to meet? Do you know? They're going to meet at 300. This is where they're going to meet, at 300. That's where they meet. So what do we have? So we have the change in position. So notice, this is x, and x equals 300. So the change in position for the cop is what? 300. And that's equal to what? His initial velocity, or let's even be more specific. Delta x for the cop, delta x for the police officer, is 300 minus 0. Right? And that's equal to what? That's equal to his initial velocity, vi, times t plus 1/2 at squared. But what's the initial velocity of the cop? 0. This is 0 for the cop. So therefore, this simplifies. We have 300 is equal to 1/2 at squared. In our coordinate system, what is the displacement of the car? Be careful. Notice when we set our coordinate system, I changed the time. And so now we're all operating in the same time frame. So that person's displacement in this same time frame is going to be 300. That's his displacement. And what time period is he going 300 meters? T plus 1. We can. The whole point is that they're equivalent. So, and what's his velocity? 30 meters per second. That's his speed, or his velocity. And so therefore, we can use this to solve for t. What do we get? We get 300 divided by 30 is equal to t plus 1, which tells us that t equals 9. And so since t equals 9, what can we do? Plug that in for t and solve for a. So we have 300 equals 1/2 a times 9 squared. So what I did here is pretty subtle. It's not necessary, but it's instructive. So we get a is equal to 600 divided by 9 squared, which is 600 over 81, which is a number. 7.4 sounds about right. Questions now. Let's take a look. I had a choice. I could have had them start off at 2 different origins or 2 different times. Okay? So what I chose was to keep the origin the same, meaning 1 coordinate system 2 times. I could have also done this with 2 coordinate systems 1 time. So you follow that. So if you notice, in time t, how far did he travel? In time t, what was his displacement? Take a look. What is t equal to? 9 seconds, right? So, in 9 seconds, he's traveling how fast? 30 meters per second. How far did he travel? 270. They're equivalent. I could have done this easily by a totally different way to do this is say, okay, the cop is here. He starts off here. And where do they meet? They meet at 300. The change in position of the car would be 270. All right, so this is 270. His velocity is 30. So we have velocity equals change in position over the change in time. If it's what? If the velocity is constant. Notice, is this, is our new kinematic equations a radically new restatement of this? Yes or no? In other words, are they equivalent? I'll get back to that question in a second. So here, this is 270, right? This is delta t, and this is 30. What do you get? T equals 9 seconds. So it's completely equivalent. One way you set your you fix your origin, you have 2 different times. Another way, you have 2 different origins, and you have the same time. So, so going back to my question. So we have delta x right? This is what you're used to before accelerated motion. This is accelerated motion. Notice, what is this saying here? The average velocity is equal to what? This is just a restatement of what definition? Average velocity is the change in position over the change in time. The second one is our new first kinematic equation. And the question is, are these two the same? Talk about it. Are they the same? And under what conditions are they the same? Be careful. Very good. Very, very good. Someone got it. So under what condition are they equivalent? 0 acceleration. In other words, if A equals 0, what do you get back? You get back the basically the rearrangement of the definition of average velocity. Does that make sense? So now here's a question. Does this basically replace this entire formalism? Is this more general? And the answer is yes. So now when you think of changing of position or the displacement, you need to think of it in terms of the first kinematic equation. We're no longer in Kansas. We are far away from Kansas. So with that, I think I want to start talking about free fall. Okay. So we've made it here. We're in free fall now. And I'm going to ask you a question, a very basic question. I'm going to take these two balls. 1, 2. And I'm going to drop them. And of course, everyone's red, so what do you expect? They're going to hit the ground at the same time. Right? Now, to within an epsilon. So they're going to hit the ground at the same time. Why? Okay. But why? Why are they going to hit the same time? In other words, why does their rate of falling not depend on their mass? And unfortunately, we're not going to be answering that question. And in fact, the answer that we give in Unit 3 opens more questions than it answers. To a large degree, it's not entirely understood why this is true. You're going to see an answer, namely that the force is directly proportional to the mass of an object, and so is the force of gravitation. So therefore, those two masses cancel out. Or in other words, your gravitational field is an acceleration field. But it turns out that that answer is not very adequate either. The reason they actually fall is very deep, and it actually ties into very cutting-edge modern physics. So we're just going to take it as an axiom. All objects fall at the same rate in a gravitational field. And so, question is, what about if I take, let's say, a piece of paper and a baseball? So, which would hit the ground first? Why? Air resistance, right? Can we show that?